Whenever an object is immersed in a fluid, it experiences an upward force due to the internal pressure of the fluid, giving it a tendency to rise or float. This tendency of an object immersed or submerged in a fluid to float is called buoyancy. Not all objects submerged in a fluid will float to the top. Sometimes the objects sink. Whether the object floats or sinks depends on the object's density, the fluid's density, and sometimes the shape of the object. To see how all of these factors work together to produce the buoyant effect, let's consider the simple case of a cylinder submerged in a liquid. We know that the pressure of a liquid increases with depth, so the pressure exerted by the liquid on the bottom surface of the cylinder is higher than the pressure exerted by the liquid on its top surface. We'll call the depth of the top of the cylinder from the surface of the liquid H1, and we'll call the depth of the bottom of the cylinder H2. So the pressure at the top surface, P1, is equal to rho GH1, where rho is the density of the liquid and g is the acceleration due to gravity. And the pressure at the bottom surface, P2, will be equal to rho GH2. Ideally, we're supposed to add the atmospheric pressure or any external pressure, so we have P1 equals rho GH1 plus the atmospheric pressure, and P2 equals rho GH2 plus the atmospheric pressure. But it doesn't really matter if we add it or not, since it will cancel out later, as we're going to see soon. Moving on, from our relation pressure equals force divided by area, we can determine the forces acting at the top and bottom surfaces of our cylinder. So the force equals the pressure multiplied by the area, meaning F1, which is the force acting at the top surface, equals P1 times A, and F2, which is the force acting on the bottom surface, equals P2 times A. The cylinder has the same surface area at the top and bottom, so A remains the same for both. The net force acting on our cylinder therefore is F2 minus F1. And this becomes P2 times A minus P1 times A. Factorizing A, we have P2 minus P1 times A. Substituting what we have for P2 and P1, we have rho GH2 plus atmospheric pressure minus rho GH1 minus the atmospheric pressure, all multiplied by A. And we see that the atmospheric pressures subtract each other out. So we're left with rho Ga into H2 minus H1. We can now see that the atmospheric pressures subtracted each other out, and all that really mattered in the first place was the pressure due to the fluid's weight. Also note that when considering pressures experienced by the cylinder, I didn't mention the pressures exerted by the fluid on the curved surface of the cylinder. Not because they don't exist, but because they are equal on all sides and cancel themselves out, thereby having no contribution to the net force. So our net force equals rho Ga into H2 minus H1. And H2 minus H1, from just looking at the diagram, gives us the height of the cylinder, and let's call that H. And so our net force becomes rho GAH, or we can rearrange that and write it as rho AHG. Taking a closer look at this, we see that AH, which is the cylinder's cross-sectional area multiplied by its height, gives us the cylinder's volume. And this volume is also the volume of fluid displaced by the cylinder. So the product, rho V, gives us the mass of the fluid displaced, and rho Vg is the weight of the fluid, which takes up a volume equal to the volume of the cylinder. The net force experienced by the cylinder is therefore equal to the weight of the fluid displaced by it. This is the buoyant force acting on the cylinder, and it points upward. It was possible to easily analyze the pressures on the cylinder and determine the buoyant force due to its simple geometry. But for an object with a complex shape, for example a rock, if we were somehow able to analyze the pressures exerted on it by the fluid, we would find that the buoyant force acting on it is also equal to the weight of the fluid displaced by it. In fact, this result is valid regardless of the shape of the object, and it's called Archimedes' principle. Archimedes' principle states that the buoyant force on an object immersed in a fluid is equal to the weight of the fluid displaced by that object. By fluid displaced, we mean a volume of fluid equal to the submerged volume of the object. Archimedes' principle applies to objects both fully and partially submerged in the fluid. So now that we know about Archimedes' principle and buoyant forces, we can tell whether an object will sink or float. If the object's weight is greater than the buoyant force, it will sink, but if the weight is less than the buoyant force, it will float. Archimedes' principle and the concept of buoyancy can be applied in many different situations. An interesting way to apply this would be to consider how many helium balloons it would take to lift a person. Helium is a gas which is a lot lighter than air, so a balloon filled with helium would experience an upward force and float in the air. How do we know this? Well, if we applied Archimedes' principle, the buoyant force acting on the balloon, which we can say is completely immersed in air, is equal to the weight of air displaced. In other words, the upthrust experienced by the helium balloon is equal to the weight of an amount of air that will take up the volume of the balloon. Since air is far heavier than helium, this upthrust is much higher than the weight of the helium-filled balloon, even when we consider the additional weight of the balloon's material. Helium has a density of approximately 0.179 kilograms per meter cube, and air has an approximate density of 1.29 kilograms per meter cube. If we assume, in this case, that a helium balloon is spherical and has a diameter of 33 centimeters, and that the average person weighs 72 kilograms, we can determine, using Archimedes' principle, the minimum amount of balloons required to lift the average person. We're also going to neglect the weight of the balloon's material to make our calculations simpler. We'll start by calculating the upthrust on a single balloon. A single balloon would have a volume equal to the volume of a sphere with diameter 33 centimeters or 0.33 meters. And this volume, according to V equals 4 divided by 3 pi r cubed, is equal to 1.88 times 10 to the power of minus 2 meter cubed. The mass of helium stored in the balloon would be its density multiplied by the volume of the balloon. So we have m equals rho v, and its weight would be its mass multiplied by the acceleration due to gravity. So we have W equals rho Vg, and this gives 0.179, which is the density of the helium, times 1.88 times 10 to the power of minus 2 times 9.8. And this gives us 0.033 newtons. The weight of air, which would occupy the same volume, can also be obtained using rho Vg. So the weight of the air would be 1.29, which is its density, multiplied by 1.88 times 10 to the power of minus 2, which is the volume of the helium balloon, times 9.8, which is the acceleration due to gravity. And this gives us 0.238 Newton. And this is the upthrust or buoyant force acting on the balloon. The net upward force acting on the balloon therefore is 0.238 newtons minus 0.033 newton, which gives us 0.205 newton. Now, the total upward force on any number of helium balloons would be this upward force on one balloon multiplied by the number of balloons, n. For a person of mass 72 kilograms, their weight would be equal to this mass multiplied by the acceleration due to gravity, g. And we can calculate this weight as 705.6 Newton. If the helium balloons were attached to this person, the upward force would act opposite their weight, reducing the effect of the weight. And for the balloons to lift this person, the force must at the very least be nearly equal to the person's weight, just slightly greater. So we have 0.205 N, which is the upward force from the helium balloons, equals 705.6. Solving for N, we have approximately 3,442 balloons. This means that we need at least this many balloons to generate enough force to lift the person.